This is part of the simplified revision series, and we have done most of the biomedical PVQs by now, starting with the aptitude, mathematics, okay, core subjects, biomechanics, biomaterials, HAP, bioinstrumentation, medical imaging, including electrical circuits and measurements. We have completed till now, right? So today we are going to do control system, simplified revision. So in fact, the syllabus says this is basics of control systems. Basics of control system. Specifically, they are referring to transfer function. Okay. But if you look at the questions by transfer function, they seem to mean anything and everything in control systems, or roughly, actually, 80% of control syllabus is there. Questions are showing up from almost 80% of control system syllabus. Okay, 80% of controls. In that sense, controls is really, really vast. Okay, but what I have noticed is, so in 4 years of PVQs, okay, there are about 12 to 13 questions. Okay, 4 years, 12 to 13 questions. Okay, that makes it roughly, 3 questions per year. 3 is actually kind of the upper limit. Okay, 3 questions per year, because this is kind of mixed with measurements. Okay, maximum 3 marks. Out of that, typically there are, 2 1-mark questions and there is a 2-mark question, or there is a 1-mark question and then there is a 2-mark question. Okay, so what I noticed is here, about 60%, that is about 2 questions, anyone can easily score. Doesn't require a lot of recall, lot of memorization and all of that. Some basics, as far as some basics, okay, you can get about 2 questions every year. Okay, so in fact, at this stage, I always suggest students to skip, okay, non-core subjects, specifically advanced topics in non-core subjects like control systems. So today I'm going to focus only on this easy 50-60% of the questions topics that show, okay, in the PVQs. So that, of course, notice IN students, EE students are starting to give the biomedical paper. Because of that, biomedical students don't want to lose an edge. Specifically, if the question is easy, you don't want to lose an edge, right? So nothing stops you from scoring those marks. And the objective of this discussion is to help you securing this 2 questions that are, let's say, really, 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 really easy and doesn't require a lot of recall. Okay, you still need to know control systems, some basics of control systems, but I'll try to make it approachable in the sense that you can answer this with minimal recall as possible. Okay, so that's the objective for today's session. And so we are going to discuss 4 years of PVQ, specifically 2020 to 2023. Okay, I'll discuss basic theory. Okay, I'll discuss PVQs and solutions. And today specifically we'll stop at easy, perhaps medium versions. Okay, let's not go to hard versions. And I specifically say that because the hard versions sometimes even there is a lot of debate on what is the correct steady state of steady state error of non-unity feedback and all that. So given that, let's not get into any confusions right now. So we'll stick to easy medium questions and we'll kind of discuss this. Okay. So first thing, let's say question from Laplace transform. So Laplace transform, I have kind of put it over here in control system so that we don't have to discuss that in signals and systems. Okay. So basics of Laplace transform. So most of transfer function, most of control systems rely on what a Laplace transform is. And for that reason, in fact, notice there is a very, very, very basic question over here. X of s is a Laplace transform of x of t, Laplace transform of derivative of x of t, assuming x of 0 is 0. Initial condition is 0. Okay. What is Laplace transform of the derivative? Does anyone know the answer to here? Okay. So notice we have if x of t, this maps to x of s, transform of this is this, then the point is, the so-called differential equations convert to algebraic equations, right? What you need to deal with derivatives, you can deal with it in terms of multiplication, addition, right? Simple algebra. So dx by dt is maps to, this is so important, x s of s, okay, minus the initial condition, let's say x of 0, x naught. Okay. Given the initial condition in this case, this is given to be 0. Okay. So your derivative is, yes, x of s. Okay. At this stage, can you recognize Laplace transform of anything else? Notice this would map to the integral of x of t. This would map to x of s by s. If there is an integral, you can replace it with, Laplace transform by 1 over s. So this is the integral, right? And in fact, this would technically map to, okay, if you take the derivative of the Laplace transform, that would map to, now you can later show that it's going to be, of course, t f of t, tx of t, okay, with a negative sign. But, let's not get into this much details, or at least know that derivative becomes this, integral becomes this. Okay, two quick questions. So let's define this Laplace transform. Basically, we'll use one-sided Laplace transform. Okay, when we say x of t, this maps to x of s. Okay, this basically mean x of s, you take the original x of t, multiply by e power minus st. Okay, and dt integrated with dt from what? From 0 to infinity. Okay, technically this is 0 plus, but let's say 0 to infinity. This one-sided Laplace transform. Okay, okay, this is the definition of Laplace transform. In fact, often knowing the definition, sometimes even if you forget some of these properties, you might be able to derive some of this basic relations or even identify some of the basic properties, at least if you know the definitions and some basic calculus. So it's a good idea to know this. And for our discussion today, okay, we also need to know some basic, basic properties of Laplace transform. In fact, more than properties of Laplace transform, uh, some basic Laplace transform. The most important property as far as we are concerned is derivative is this, integral is this, right? That we have seen. Quickly recall some standard Laplace transforms, okay? So delta of t, if you take Laplace transform of that, this goes to, what is the Laplace transform of delta of t? This goes to 1, okay? And then u of t, what does this transform to? 1 over s, fine. This goes to 1 over s. We might also need a ramp and a exponential, okay? So we'll come back to that in a moment, okay? At least these two for now. Okay. Now, the first two things, derivatives become, sx of s, integral become x of s over s. Often there are questions from initial, questions about initial and final values, okay? So if x of t transforms to x of s, if you know the Laplace transform of a function, finding specific values of the function is very easy. In fact, so this is specifically given given the Laplace transform. That is, let's say you don't know this, what I'm writing in gray, you don't know that. If you know x of s, okay, you can very easily find out specific values of x of t. Okay, those specific values happens to be, one is you can find out the initial value. You can also find out the final value. That is what happens to the value of x, okay, at 0, basically 0 plus, okay, and then what happens to x at infinity after a long, long time. Okay, let's not have that confusion over 0 minus 0 plus at this stage, okay. Let me just say this is 0, okay. So this happens to be, you can get that from x of s. How do you get that? That equals, okay, in fact, both of that you are going to get from x of s. Let's in fact give a little more space to this. These are two specific values. I'm not talking about finding the actual function corresponding to this transform. I'm just talking about two specific values, okay. Let's be very clear about it. Easy to find two specific values. This is easy to find two specific values. Specific values under certain conditions. Okay. Of course, like all math theorems, there are like certain requirements, but under certain conditions, let's not worry about that to make your life simple and easy at this stage. So this is, both of these are limits. Okay. This is limit yes tending to something. Okay. This is also limit tending to something. Again, this you can get from x of s. In order to get the values, what you need to do is to multiply this by s. To get the initial value, you have to substitute or let s tend to infinity. Okay. To get the final value, again, you have to multiply this by s, multiply the Laplace transform by x, and let s tend to 0. Okay. Again, this is not a delta. I'm writing that's an s. Okay. S tending to 0. So from the transform, you can find the initial value by multiplying it with s and let s tending to infinity. Notice this is also a function of s. So let this function of s find the limit of that function when s tends to infinity, you can get this. If needed, you can use L'Hopital's rule. Okay, now the ball is at your court. Sir, I'm weak in finding limits. Fine, just use L'Hopital's rule, whatever it is, whatever is needed, you can use that. And this goes by the name initial value theorem. This goes by the name final value theorem. So initial value, let s tend to infinity. Final value, let s tends to 0. Okay. Now let's look at this specific question. A unit step input is applied to a system with impulse response h of s. H of s is this. Okay, at t equal to 0. Okay, fine. The output of the system y of t at t equals 0 plus. Okay. Now, quickly, this is telling you what is the value of the output, particular value of the output. They are not asking you for the entire function. They are asking you for a particular value. You quickly know that this has to do with final value theorem. Okay. And we just noticed this in one of the PVQ discussions. And this impulse response also happens to be the transfer function. Very recently recalled it. Okay. I'll quickly also show you what that is. So essentially what they are asking for is, notice your y of s in general is h of s, x of s. By definition, this is transfer function is y of s over x of s, right? This is the transfer function. How that happens to be the impulse, I'll explain that in a moment. But let's say this is the transfer function, or this by definition is a transfer function, ratio of output by input, Laplace transforms. Okay, and this happens to be, okay. Notice, so y of s is h of s into x of s. What they are given us, this unit step input is applied. We just discussed u of t maps to 1 over s, right? So your y of s is h of s is 1 minus s by wz by 1 plus s by wp. Okay, that is your h of s. And then your x of s happens to be u, right? So the transform of that corresponds to 1 over s. If you want me to color code this quickly, let's say x of s. X of s happens to be 1 over s. Okay, because the input happens to be a step. Okay, so we know the Laplace transform of the function, we need a specific value at 0 plus. Final value theorem, fine. So notice at this stage, your y of 0 plus equals limit s tending to infinity s times y of s. Be careful about that. Okay, this is s times y of s. Sometimes you tend to miss the s. Okay, so this is yes. Okay, there is a 1 over s there, and then this is 1 minus s by wz by 1 plus s by wz. Okay, and of course, this is in the limit s tending to infinity. Let's find little space, some space over here. This is s y of s. That happens to be limit s tending to infinity. Okay, I wrote FVT. This is IVT. Okay. So one of the value theorems, initial final. Okay, this is t 0 plus, right? So this happens to be this yes will cancel with this yes. At this stage, you go s tending to infinity, 1 minus infinity by 1 plus infinity. You can do L'Hopital's rule or quickly pull out this yes. Okay. And quickly pull out this yes. And then, of course, cancel it. Okay. 1 by s, of course, s tending to infinity would be 0. That will also go to 0. Okay. This term goes to 0. This term goes to 0. So what is left is wz by wp. Okay. That would be w minus of wp by wz. I suppose the answer is this. 1 over wp is in the denominator, right? Goes to numerator, becomes wp. The answer is this. Okay. Okay. Now I need to let's also quickly see why this impulse response is this transfer function. Okay. Again, we already saw it that day, but let's also, for completion's sake, this is a very important property of Laplace transform. One is I defined, you know, transfer function h of s. By definition, let's say this is y of s by x of s. Okay. Now, sometimes they call it h of s. Sometimes, based on the application, there is this g of s. Sometimes they refer to this as t of s. Okay. And let me also, this is the transfer function. At this stage, one of the simplest traps people fall for is the inverse of this. That is x of s. Okay. Let's also, kind of write it down over here separately. This is a common trap. Inverse of this is x of s by y of s is the inverse transfer function. Okay. This is the inverse transfer function. Often the simplest trap set in a question, gate question, is you find the transfer function or they have put find the inverse transfer function. People end up finding the transfer function and checking the transfer function, but what they are asking for is inverse transfer function. It's a very common trap. So I am kind of highlighting that over here. Okay. Now, this means your h of s is y of s into x of s, right? Very, very, very important property of Laplace transforms. Okay. In fact, it's kind of convenient to write it uh, from left to right. Okay, I'm trying to end up writing it from right to left, but let me just write it conveniently again. The final form should be right to left, right? So you have your h of s. This is nothing but y of s into x of s. So far, the same thing that we have seen, right? y of s into x of s, right? This, notice at the end of the day, this is a function of s that can have a function in the time domain. So if you ask this question, hey, for which function if I take Laplace transform, I will end up with this. Specifically, for which function if I take the Laplace transform, I end up with this product of x of t and y of t, right? That happens to be, does anyone know the answer? I should end up with product in the transform domain. In the time domain, what would that be? This is supposed to be a convolution. I mean, what is convolution? Every year, almost there is a question from convolution, discrete or continuous. Okay, so I'll discuss that in signals and systems. But notice, this is going to be from convolution. Okay, and let's just for now write this as y of t convolved. That star is convolution with x of t. Okay, so convolution becomes a product in the transform domain. If you take Laplace transform of a convolution, it becomes just a product. In fact, this is one of the things that one of the properties of Laplace transform that really makes your life very, very easy. Okay. At this stage, whether you're watching signals and systems or not, whether you're attending signals and systems or not, let me quickly tell you. So convolution becomes a product. So often in gate, they give you two band limited signals, x1 of t, x2 of t. And the real signal of interest is a convolution of the two. Okay. So x1 is band limited, x2 is band limited. The signal of interest is the convolved version of x1 and x2. Okay. So in the transform domain, simple product, this convolved function is also band limited, specifically limited by the smallest band, because it's a product of the two. Wherever the frequencies are zero, product of the two frequencies, one frequency is zero, the product is zero. So the convolution is also band limited, the band limit being the smallest of the two. Okay, that's a very, very, very typical gate question. Whether I will have time for that, whether you will have time for that or not, I just put it up over here because it's very, very important. Okay, that's one thing. And now, what are the consequences of this? So notice your y of s, x of s is your h of s, right? We have already seen that um, this function. Okay, we have already seen that delta of t goes to 1. Okay, and u of t transforms to 1 over s. Okay, that means if surface 1, that is x of t happens to be delta of t. The name for this is impulse response. Impulse response, right? Your why impulse transformed function of the transformation of the impulse response happens to be that also happens to be the transfer function, because x of s is 1 in the specific case. When x of s is 1, that is in the specific case when you are looking at the impulse response, you are you know you are getting the output to be the transfer function. Okay, so your transfer function happens to be also the Laplace transform of the impulse response. Okay, that is why impulse is an output specifically for an input, that is delta. Okay, this will be h of t. Okay, where h of t is the Laplace transform of h of t corresponds to h of s. Okay, so you could also of course notice your h of t will transform to h of s. Okay, bottom line, transfer function is the impulse response. Writing it in the top line, okay, but that's a bottom line. Transfer function is the impulse response. That is why they are saying a impulse response apply to a system with impulse response. They have given it in the yes domain. That is, they have given the transfer function, and we could do whatever we get here. Okay, so now we can take the transfer function. Now new input happens to be okay. The response that we are looking for is not impulse response. What we are looking for is a unit step input response, right? So our x of s is 1 over s, and we'd apply this by initial value here. Okay. Again, an important detail, which is a typical concept of interest in gate papers. So I kind of pointed out that one also. Transfer function is the impulse response. Okay. There is this one more question on Laplace transform. Does anyone know the answer for this? Probably if you're from instrumentation, electrical engineering, this is a cakewalk, right? So notice while I wait for an answer, in fact, Laplace transform is used to represent exponentials. And with the Euler's theorem, essentially we can represent oscillating exponentials, right? E power minus at transforms to 1 by s plus c. There is a singularity at s equals minus a. The language, in this function, there is a pole at minus a. Okay. And Laplace transform represents exponentials. Okay. And this function singularly represent this exponential in simple English. Okay, which is why your differential equations become algebraic equations and all that. Okay, there is a singularity here. If you substitute s is minus a, this is going to infinity, right? There is a pole here at s equals minus a. Very, very simple terms. Okay, this function, time function, is singularly represented by this transform function. Okay, it is singularly represented. You could kind of use that. In fact, this function is in the transform domain is 1 by s plus a. The point of that being, now any function that, if we take any function, again, I want to try to stay in the safe route. If you look at this, okay, any function that grows slower than e power minus at will remain stable. Okay. In fact, the product of this should at max be like a unity, should at max be step, right? So till then you are in the safe zone. So the regions of convergence has to do with that. So let's not really worry about this. Okay. It has to do with what happens to this product. Okay. How fast is a function growing with respect to, a given function. Okay. E power minus at or e power minus st doesn't matter. In fact, if you know that the Laplace transform is this integral, right? So you're essentially asking how fast is a given function growing with respect to this. Okay. Based on that, you can quickly answer this. But right now, let's say from recall, uh, this is a this is at +1, right? Or this is at -1. There is a pole here at -1. So it's not with respect to left or right. It's with respect to left or right. With respect to -1. So that's why I kind of ruled out ABC. But in either case, the imaginary axis. So to the right of -1, imaginary axis will be there. To the left of -1, uh, left of +1, imaginary axis will be there. For that reason, D is the answer. Okay. You could quickly answer that if you understand either this transform or this definition as a dot product. Okay, this integral happens to be, this is how you do dot product of, how to do dot product of vectors. There is a way to do dot product of functions. Okay, the dot product happens to be this integral or happens to be integrals. So if you either appreciate that or this, the answer here is fairly easy, but that appreciation is really far away. Okay, and I don't want to confuse you. So often any explanation I give at this stage ends up being, counterproductive and ends up as a confusion. So let me avoid that, but I can give you one pointer. I think there is a video by three blue, one brown, or one brown, three blue, something like that. What is a Laplace transform? Why didn't they teach Laplace transform this way, or why didn't they, this is what they should have taught in Laplace, in school about Laplace and something like that. There is a video by, three blue, one brown, I think. Okay. You could take a video, you could take a look at that video. to actually intuitively answer this question. Okay. Other than that, let's not spend more time here right now. Okay. This is sort of, let's say, somewhat advanced. Okay. Let's move on. Consider a type 2 unity feedback system. The intersection of the initial minus 40 dB per decade segment of its Bode plot with a 0 dB line occurs at a frequency of 2 rads per second. The acceleration error constant of the system K is. Does anyone know the answer here? So, this whole thing, that whole text in simple English, that whole text in simple English, this is in engineering language. There is a lot of jargon, right? Type 2 unity feedback system, intersection of minus 40 decibel per decade in the Bode plot with the 0 dB line occurs at a frequency of 2. That's a very complicated engineering language. Okay. In very, very simple English, what they are saying is root Ka, okay, square root of Ka happens to be, in simple English, square root of Ka happens to be 2. What they are saying, that whole big thing, right? All the words here, type 2, unity feedback system, okay? All of that put together, intersection of the initial minus 40 dB per decade line of its Bode plot, okay, with the 0 dB line occurring at a frequency of 2 rads per second. All of that put together, say root Ka is 2. Of course, that means right now anyone can answer K happens to be 4, which is what they want, right? K happens to be 4. We can answer it at this stage, but the real question is, can we understand this English? Okay. I can give you some minimal pointers. I'm not going to explain what a Bode plot is. Okay. And it's a function. Okay. It's a function of frequency. It's a function of frequency. In that, there are 3 things. There is a type 0 system. There is a mentions type 1, type 2, right? Yeah. There is a type 1 system. Then there is a type 2 system, as this question asked. Okay. So what you're looking for is, this is a function of frequency often in this. Okay. Initially, let's say for a type 2 system, it's going to go down, and it can change as it proceeds further. Okay. Depending on what the entire Bode plot is, it can technically be this way, this way, this way. It can do anything here. Okay. But initially, this is going down, and that initial slope, it, in fact, this is 40 decibels per decade. This is in the log scale. Okay. 40 decibels per decade. That is given to be, in fact, that says this is, uh, that's a second order system. Okay. So 40 decibels per decade has to do with the slope. What we know is that, so when the Bode plot of that type 2 system is plotted, this point where this is in this axis is in all the axis, this is in dB. decibels. You know what decibels is, so I'm not going to again explain that. So the 0 decibel is this, that x-axis line or the omega axis line, right? Wherever this initial green line, if you extend it, that is why I've dotted it. Wherever that intersects, that happens to be square root of Ke. This is also referred to as the acceleration error constant. Okay. A type 1 system, again, a similar thing is going to happen. Initially, this is going to go down slower as to, this will have a lower slope. Okay. This will go down at 20 decibel per decade. That again, most of you know. So if you kind of extend that initial line, let's say this is slow enough. Okay. The point that you get here goes by the name velocity error constant, kV. That happens to be kV directly. That frequency happens to be kV. Okay. And for a type 0 system, it should initially be straight line. And then it can change this way or it can change this way. Let's not worry about which way it's going to change. Okay. Uh, Here also, in fact, initially it needs to be going down at 20 decibel per decade. After that, it can change this way, remain this way. It can change this way and all that. But initially, it's going to be a straight line there. Okay. And in fact, I have to, let's say, after some point, let's say it kind of changes. Okay. So that's why I'm drawing just the initial line. You can get the position error constant from here. 20 log this value, starting value happens to be 20 log of Kp. So it's possible to get error constants from Bode plot. Okay. Bottom line here, easy to find error constants from Bode plot. Oh, yeah, just as we did here. For type 2 system, error constant is square of this number wherever it intersects. For type 1 system, it's just that number wherever it intersects. That is, and for a type 0 system, this is the initial value itself will be 20 log Kp. Okay. And what are these error constants? Let's not get into that detail, but at least this is position error constant. This is labeled as position error constant. This is velocity error constant. This is acceleration error constant. Ka happens to be acceleration error constant. Okay. Again, Bode plot is there in electrical circuits, is there in control systems. At least one in 2 years, there is a question. Okay. At least you need to know this much. So, which is what I said in simple English, root K is 2 and finding K is fairly easy, right? Similarly, let's say they give a type 1 system, intersection is some number 2. Answer, what is the velocity error constant? Answer is 2, right? Okay, let's go to the next question. Closed loop characteristic equation of a system is given by, they are given a polynomial, the frequency of oscillations of the closed loop system at steady state. So again, the theory here is if we had to start from scratch, this is going to be like take a lot of time. Okay. To simplify your life, what I'm going to say is let's label this frequency, the frequency of oscillations. It let the frequency of that frequency, let's say this is omega I, there are frequency of oscillations. Okay, frequency of oscillation. Let's say this is omega I. Okay, let's not even complicate it with multiple frequencies. The frequency of oscillations of this closed loop system at steady state. Okay, in simple English, that frequency is a root of the characteristic equation, closed loop characteristic equation. Okay, so omega in very, very simple English, if this is a case, j omega is a root of the characteristic equation. Root of the characteristic equation. There is also a characteristic equation in linear algebra, right? Kelly Hamilton theorem on that. But this is class characteristic equation and controls. Okay, whatever it is, they have given it there. If it is oscillating at steady state at a specific frequency, that should be root of this characteristic equation. So now our task boils down to verifying whether the given numbers are roots of this equation. Specifically, be careful. This is not omega, this is j omega, which is why it has a possibility of canceling out. Okay. This is j omega. J omega is a root of that CE. Okay. So we have to quickly substitute j omega here and see if things verify. So j omega here is j. If you substitute that in characteristic equation, you have j power 4 plus 2j cube plus 8j square plus 8j plus 16. Okay. And j by definition, this is Dr. J. What is j? J by definition, square root of minus num. So that means if you square this, j square is going to be minus 1. Okay. J cube. J cube. What would be j cube? Actually, we have a lot of space over there. If you put my figure face over there, so my face is going to get cluttered with the J, J, J and all that. So let's put it somewhere over here. J cube happens to be J square into J. So minus 1 into J, that is minus J. And J power 4, we need at least power of 4 over here. That is J square into J square, minus 1 into minus 1, that is plus 1. Right? So you can simplify this. This is 1 minus 2j minus 8 plus 8j. Minus 2j plus 8j won't cancel. they won't cancel. The J will remain. Whatever happens to the other terms, that J will remain, right? So you are not getting a 0 in the RHS. If you check the LHS, substitute that, you are not getting a 0. It's not equal 0. So this is not an answer. If you substitute 2J, if you substitute 2J, 2J power 4, okay, that is 2 power 4, 16, J power 4 is plus 1, plus 2 into J cube, okay, J cube is minus J, 2 into 2 cube, again that is a 16, I suppose, okay, plus 8 into 2J square, okay. So 8 into 2 square, that would be 32. J square is minus 1. So this number is minus 32. Okay. 8 into 4 into J square. That's so I got a minus 32. Yes. That will be 16J. 8 into 2J. 16J plus 16. There is a JJ cancelling. Yes, imaginary parts disappeared. Real parts also disappear. Plus 16 minus 32 plus 16. That equals 0. So this is the root and this is one of the options. So in short form, if you write this as f of s is 0, okay, what I have shown as f of j is not equal to 0, okay, f of 2j equals 0, and can we quickly say is f of, I think this is an, let's make our life simple. This is an MCQ. We found the answer, but quickly you can verify f of 4j should not be equal to 0 and f of 8j should not be equal to 0. Okay. Okay. Again, this is what happens in terms of very simple English. At least if this question repeats, in simple English, this is what they are asking. So you could quickly answer that. Again, there is time response and signals and systems. There is time response and control system. So I at least put some of that over here. M1, M2 are roots of the characteristic equation of a linear second order physical system. Match the nature of the roots with the natural response of the system. The roots tell you what the natural response is. There is, if you don't force it, what the system will naturally do in simple English. Can we map this? It's also there in engineering mathematics. Underdamped system, critically damped system, overdamped system, undamped system. Yeah. This is there in engineering math, differential equations, right? Engineering math, S&S, although time response, second order time response controls, and electrical circuits and second order systems, there in second order systems. So, my suggestion is always no till first order systems in and out. Second order systems, if we have the time, learn that. Okay. But knowing if you know till first order systems in and out, you can do very well and get biomedical paper. Okay. So, but this is fairly easy, right? So real and distinct, this is going to be, of course, over damped. Equal, this is often if you're designing, the design typically involves, a good design typically involves a critically damped system. And any complex roots, this is going to be undamped, right? So, so your characteristic equation, second order, in very, very, very simple terms, S square plus BS plus C equals 0. And familiarly, you will put a here, right? Whatever that characteristic equation we saw earlier, let's say that characteristic equation, we had a fourth order characteristic equation, right? For a second order system, we have a second order characteristic equation. This is a polynomial. You can solve it. You can find the roots. This is minus b plus or minus square root of b square minus, 4ac pi, everything by 2a, right? You know the roots of this. If those roots happens to be real and distinct, get a overdam system, um, equal this, okay? Very quickly, let's write this in this form. The roots are m1, m2. So they satisfy the characteristic equation. So the polynomial has to be of this form. Then kind of overlook that a over there, right? S minus m1 into S minus m2. That is, if you substitute m1 here, it goes to 0. If you substitute m2 here, it goes to 0. If you remember anything from differential equations, you know that. So this characteristic equation shows up in the denominator, right? So if you know anything, remember vaguely from differential equations, that means okay, your solution could be of three types, right? In fact, I do have some space over here. The three cases given are real and distinct, and then critically damped, and then underdamped. It's physically known as, this is m1 not equal to m2, real and distinct, right? Let's say two real numbers, m1, m2. Your solution, say if it's a differential equation, your solution would be typically e power m1t. Okay, combination of this and this, m2t. And of course, you can have some initial conditions, right? So typically it's two exponentials. And if it's physical system, M1 and M2 will be negative for a physical system. Okay. They will be decaying exponentials and they will quickly drop down as exponentials. If it is critically damped, you can have a constant if here if you want, okay? If you want it to be critically damped, solution is going to be A e power, this is where M1 equals M2, right? Whether again it's complex, imaginary, there is a question over there, okay? But in simple terms, this M1 not equals M2. Okay. In this case, your solution, what kind of a solution will you have here? There will be this, of course, M1 is a solution, we'll have that. Okay. Because it's a repeated root, you will have this e power t e power M1 t. Oh. And for an undamped system, and M1 and M2 are complex. Again, let's say so notice this is an exponential, this is an exponential. If M1 and M2 are real, okay, this is an exponential. This is also sort of an exponential kind of dominate. Just that only there is t is there. This is also an exponential, but it's slightly somewhat special. If it's undamped, again you have your y of t equals a e power complex number times t. Okay, as b e power a complex number times t. Okay, so in this case you have m1 and m2 or complex. Okay, if M1 and M2 are complex, if you vaguely remember, if you use Euler's theorem, this is e power j theta kind of, there is a j there, square root of -1 over there. If you use kind of Euler's identity, you don't have to panic. Okay, this is a very, very basic, most beautiful equation in math, right? Euler's identity, you can quickly see that these are sinusoids. These are oscillating things. These are sinusoids. You can quickly see that these exponentials start oscillating. Right? So this is, it's not damped. It's going to keep on, it won't dampen. It'll keep on oscillating. Will keep on oscillating. Okay. And technically, I can connect what I said here with the Laplace transformers. Or a special case of this will happen to be the Fourier transform. And then, so if you can represent sinusoidals, you can represent exponentials and all that. Kind of briefly mentioned about that initially, but the connection is very, very, very close. Okay. In fact, if you start looking at a second order system, you can easily start making all the connections. But right now, Euler's identity, you can quickly say these are both of them is going to oscillate. There are sines and cosines over there. Okay. And Yeah, they have given a second order system in a PVQ, right? So this is system described by the following differential equation: 0.01 second derivative of y plus 0.2 first derivative of y plus y. Y is a function of t. X is the function of t. Notice this is an input. X of t is the unit step input applied at t equals 0 seconds to the system. Magnitude of the output t equals 1s. So let's recall some basic things. If you know the transfer function, so in fact, if you take Laplace transform on both the signs, okay, here I think you'll have to presume initial conditions are 0. Presume 0 initial conditions. Okay, it's not given, okay, but not necessarily 0, but this is the case. If you take Laplace transform, what happens here is 0.01 is the second derivative, so that is s square y of s. First term. Initial condition, slope change, initial value and all that, let's say 0. Plus 0.2 first derivative of y, so that is s times y of s. Again, this is something that we recalled, or at least we saw today, right? Term is y of s equals 6 times x of t. Is x of t given? Is x of t given? X of t is a unit step input. It's a unit step. You also know the Laplace transform of that. 6 is a constant, okay? The Laplace transform is linear. You can pull out that constant. So suddenly, sir, convolution. So if this is if this is a product, will that be a convolution? No, this is linear, so you can pull out constants. So Laplace transform of x of t is, oh, this is just x of t, right? X of s. Yeah, let's have it at x of s right now. Okay. So your y of s, if you take it out, you got here I have 6 x of s. Okay. Let's leave it a little more space, add a little more contrast. Your y of s, I pull that out. Right hand side, you have 6 into x of s. Y of s is common in the LHS, right? I take it out, you have rest of the terms. Rest of the terms, I'm going to bring it to the right hand side. So they will all come to the denominator. And what you have here is, again, let's conveniently write it here. They're all going to come to the denominator. What I have here is 0.01 s square, okay, plus 0.2 s plus 1. If you recall, O of t goes to 1 over s. So I can replace this x of s with 1 over s. So it's kind of looking like child. So let's give it some shape. Okay. This is y of s. Given this at this stage, technically, if we can do the inverse Laplace transform, you know y of t, right? So here you need, oh, you need the magnitude of the output at t equals 1. It's not 0 or infinity. You cannot use initial or final value theorem. This is some bit value. There is no bit value theorem, right? But here is the development so far. And the idea is y of s. If you could somehow take the inverse Laplace transform, you know what the y of t is. How do you take the inverse Laplace transform of this? How do you take the inverse Laplace transform of this? Okay. In fact, this denominator, the term that we have here, what we typically refer to as the characteristic equation. There was this characteristic equation, the previous two questions, right? Here there is a characteristic equation. Here there is a characteristic equation. Typically, this denominator, excluding x, denominator of that y of s is referred to as the characteristic equation, at least in this context. Okay, this is a CE. Yeah, in war there aren't many tactics, right? Divide and conquer, simple amateur general, divide and conquer. Notice. So, for can this be divided? This is a square. Can we simplify this into something of? Uh, can we somehow simplify this? Yes. Notice that happens to be okay. No worries. Fix. Can you do? Is there a square of that something? This is 0.1 s plus 1 whole square. If I square this, I'm getting 0.01 s square plus 0.2 s plus 1 square. Okay. It's a very simple algebra over there. Let's also, let's give it. No, no, just write it. A of s happens to be so far 6 by, there is a s sticking around from this thing, and then this happens to be 0.1 s plus 1 whole square. So I'm going to write this as 0.1 s plus 1 into 0.1 s plus 1. Can anyone say poles of y of s? What are the poles of y of s? Poles or that which make the function infinite, function singular, denominator, roots of the denominator. The poles of this, the roots of the denominator, or in fact, if I have to write it more conveniently, I'll also write this as s minus 0. 0 is the root of the denominator. So this is the poles here would be, of course, the 0. The root of this, that would be minus 1 by 0.1 and minus 1 by 0.1. There are two repeated roots, repeated poles, or there is a second order pole at 0.01. So what are the poles of this? So poles are 0, minus 10, less 10. If you know the poles of y of s, writing down y of t is fairly easy. I already did it. If you know the roots of the characteristic equation, that is, the pole, writing down y of t is fairly easy. Just e power that root power some constant times e power that root, constant times e power that root, constant times. It's repeated slightly different. Okay. You have to account for that repetition. Again, it's constant times e power that root, right? Same story here. Okay. In fact, for the discussion, it kind of helps to know, helps to get one more line. I don't want to go to one more new page. So I'm going to write this as minus 10 there itself. Okay. I need a little more space. So given the poles, you can easily write down what y of t is. Okay. 1 second. Minor technical glitch. So the function is going to be e power this. This will have e power 0t. This will give e power minus 10t. And because this is repeated, that will give a e power minus 10t t times that. Okay. Now the poles, you can easily write down the solution. It's going to be a combination of these three things. What do you mean a combination? So this function plus this function plus this function. 3 exponentials. And things are repeated, so I put that t. In fact, the repetition, the t kind of over there. Okay. It's repeated. There are two roots, so the t shows up from there. Which combination is a weighted combination? Which weighted combination? There is a constant uh, constant. I'm more concerned about explaining some basic terminology, next year's question compared to answering this question. Okay, so I'm taking a little more time. Some coefficient ABC are constants. So if you know the poles, you know the solution. It's a combination of 3 exponentials in this case. That's what I have been doing it, right? I already did that. M1, M2, A, it's a summation of 2 exponentials. Of course, the weights are different. Weights A and B. Let's say the coefficients A and B. Again, it's 2 exponentials. A repeated, I put a T over there. Right? If it's repeated, I put a T over there. Again, summation of two exponentials. Of course, the exponential happens to be complex exponentials. So Euler's identity said, oh, this is sinusoids and cosines. I'm doing the same thing over here. If you know the poles, you know the solution. Poles are roots of this. So there is one question here. So how do you find the poles of this? Poles are roots of the denominator. What makes the denominator 0? If s is 0, the denominator is 0 here. If s is minus 10, the denominator is 0.1 into minus 10 plus 1. That is a 0. How do I find it? Okay, this is set this to 0. S minus 0 equals 0. You know s is 0. Okay. And then set this to 0. Set this to 0. 0.1 s plus 1 equals 0. So your s is minus 1 by 0.1. That is 10. There is a question. I suppose that question is answered, right? Yeah, how did you find the poles? And again, what is the root of that? It's minus 10. Good question. Okay, simple answer. Okay. Fine. I answered that. Notice if you know the poles, you know the function. At this stage, again, you need to know some basic terminology. So roots of the numerator will be called as zeros. There are no zeros here. There is no solutions of the numerator. Only the denominator we have poles here. Okay. Is this fine? Okay. Oh, I said that if the poles are this, the solution is going to be this. How do you properly do that? By taking the inverse Laplace transform. And how do you take the inverse Laplace transform? For polynomials, you have to do something called, you have to do it by parts. You have to separate it by parts. That is, you have to separate y of s as as an unknown by s, okay, as an unknown by 0.1 s plus 1, okay, plus an unknown by 0.1 s plus 1 whole square. You have to do some separation of parts here. You have to find the ABC. That is how, you know, uh, you technically do it. And there, hoping in the hopes of, in the hopes that finding inverse Laplace transform of this is fairly easy. Of each of these terms is fairly easy. When the function is undivided, it's very hard to do the inverse. When the function is divided by parts, divided into parts, individual parts Laplace transform is fairly easy. This is the idea behind here. In fact, this transforms to that, this transforms to that, this transforms to this. Notice 1 over s is e power 0t, the exponential that doesn't decay. That's a step. This happens to e power 0t happens to be u of t, step function. One more quick connection. E power minus at transforms to 1 by s plus a, which is what I am kind of using here. Just that it's a second order pole, second or repeated pole. So you have to slightly deal with it carefully. I said this exponential transforms to 1 by s plus a, right? Notice if a is 0, e power 0t is essentially a step function equals u of t, and it transforms to 1 by s, right? E power 0t is essentially a step exponential that doesn't drop, that doesn't decay or doesn't explode, remains a constant, right? That is one other connecting detail, okay? Just if you want to slightly appreciate this. So I ended up taking Laplace transform of this function by dividing into parts, dividing and conquering it. Okay. And I have to explain one thing, and I'm trying to see how to. So far, so good. Or things slightly, going out of page. I try to constrain it to one page. Okay, there's a lot of theory here, but so far so good. Poles are roots of the denominator. If you know the poles, you know the function. Yeah, that's all I have said so far. I'm going to write something on top of what is written there, and I'm going to erase it off. Okay. Finding this constant is very, very easy. This function. You have to remove the singularity corresponding to that pole. I remove the singularity. Substitute s equal to 0, the pole value. If you substitute x equal to 0, you can quickly see this is 6 by 1 into 1, 6. That happens to be the constant a. That constant a is fairly easy to find. That happens to be 6. This happens to be 6. Okay. This is a trick that we use to find the coefficients in the Taylor series. Same trick. This is a trick that we use to find the coefficients in Lorentz series. Residue of a function is also that trick. Okay. Because, okay, let me just write down that one trick separately. You have a general function y of s equals um, equals say s plus a by s plus b. Okay, there is some constant over here. Let's call it k for convenience. Okay, you want to split this up into 1 by s plus a some other constant by s plus b. You want to find this constants, right? So that notice this individually this transforms to a e power minus at. This transforms to b e power minus bt, right? So y of t is a solution of this. This you can do that, but in the you have to be able to find that constant in the process, right? Finding that constant is fairly simple. Your a, let's again give some colors over here. This is slightly more involved for a second order pole. If there is a square here, there is slightly involved. So it is the previous question. That's not complicated. But if this is the case, a is fairly easy. Even though ab is fairly easy, a happens to be take your y of s, remove the singularity, remove that pole. How do you remove that pole? Just multiply that by s plus a. You have removed the singularity. Now evaluate this at the singularity. Evaluate this at s equals minus a. Okay. For example, let's say this is x by s plus 0. Okay. So the first thing that I do was move the singularity, evaluate it at s equals 0. Evaluate y of s at s equals 0 after removing the singularity. That is, if you substitute s is 0 here, you get a 6. That happens to be the coefficient. Okay. Because it's a simple pole, it's very easy to find. This is B and C are slightly complicated. You cannot find that, but finding this, this is a non-repeated root that is very, very easy. Remove singularity, evaluate it. What is B? Again, the same trick. Remove singularity, evaluate it. B happens to be take y of s. Remove that singularity. How do you remove the singularity corresponding to coefficient B? By multiplying by s plus b. So s plus b will cancel. In fact, if you want me to actually show it this way, notice if I take y of s, if I remove singularity, I'll have s plus b here. Okay. I'll have s plus b here. If I remove it, I isolated b. Then if I evaluate it at s equals minus b, right? I have made this term 0. I have made that entire term 0. What is left is just b. In the RHS, in the LHS also, what should be left is just b. Okay. That is a trick that I am using. Partial fractions. Okay. It boils down to that. So okay. Let me repeat this once more. And this time, so you take that function, remove the singularity, evaluate at the singularity. Okay. Let me do that process over here. Okay. This time I'm not going to erase it. I'm going to leave it cluttered. I take y of s. I remove the singularity. I want to find p. Then I evaluate it at singularity. When I remove the singularity, okay, multiplying RHS by s plus b, notice the singularity cancels. So this is the part where I remove the singularity. I remove the singularity. Then I evaluated it at s equals minus b. If I substitute s equals minus b in the RHS, this term is 0. Evaluated it, if I put s is minus b plus b is 0. So a times anything times 0 is 0, right? So that term disappears. What I am left with is b. I am finally left with this b, just b. Okay, this trick is so important. So I kind of spend some time explaining it. That is what I did here. So finding that coefficient is very, very simple. So we have a constant, e power 0t is a constant. So 6 plus some function that is decaying very fast, minus 10t. Another function that is taking very fast, minus 10t multiplied by t. So now, can someone find what is e power minus 10t? In fact, substitute t is 1. What is e power minus 10? You do have a calculator. So after a long time, I am this calculator. Can someone find what is e power minus 10? 4.53. You are missing some decimals or you are adding some decimals. Be careful. 4.53 into what? 10 power into 10 power minus 5. Rounded off to 2 decimal places. Anything in the power of minus 5 will not show up in the answer. For that reason, this is negligible. 10 power minus 5. This is 1 into 10 power minus 5. Whatever is the coefficients are not going to be 10 power of million and all that, okay? For the numbers given here, they will be in the order of 1. BC will be in the order of 1, just like A was in the order of 6. A was 6, right? Order of 1. So BC won't be too high. BC will be around something in the order of, minus 2, minus 6, 6, 1, 10, minus something in that order. It won't be like 10 power 4 million and all that. It won't go. Because of that, this term is essentially 0 up to 2 decimal places. This is 0 up to 2 decimal places. What you are left with is 6. Okay. So that answers this question. Okay. The answer here is 6. But in the examination, this can be done really, really faster than what I did here. I was trying to introduce many jargon here. Okay. So what is YFS? 30 seconds or something like that. All of you can do that. Completing the square, recognizing a repeater to root, 30 seconds, all of you could recognize that, right? So finding the poles, you know the poles. If you have completed the square, you know the poles. 0, minus 10, minus 10, you know that. If you know the poles, you know y of t. You can write it down. Another 30 seconds. In 2 minutes, you can write down y of t. 30 more seconds, you can recognize the coefficient of e power 0 t is 6. Remove that singularity, substitute s is 0. Fortunately, you're substituting s is 0. You're not substituting s is 10. At least that will take a minus, 1 minute or something like that. So in 2.5 minutes, you recognize this coefficient is 6. Rest of the coefficients, irrespective of them, they are all decaying exponentials, fast decaying exponentials. In a span of 1 second, they will go to 0. You can recognize the answer is 6 in 2.5 minutes. Okay. But in the process, we learned, in fact, where is this characteristic equation? An actual example of that. Okay. Let's put it over there. What this characteristic equation is, and then how that is related to those solutions. Okay. Why this Laplace transform e power minus at equals, transforms to 1 by s plus a. How that is kind of used to find solutions of first order, second order differential equations. Okay. And then I also explain how do you divide and conquer, specifically this partial fractions. Okay. And if you know this, technically you can, typically you can answer one question, not necessarily in controls, but somewhere in the paper, there is a first order system, question from first order system. There is a question from second order system. You can actually answer that. And what is required is some basic engineering mathematics, not very complicated controls or signal systems or properties of Laplace transform. Some basic things, you can technically answer this. Okay. Okay. That is why I explained this so far. And it also kind of connects all of the things that you learned, right? There is a Laplace transform, where is the solution? Okay. With that, what is the next question that I have? Okay, I have two more questions. Okay, so non-unity feedback system is this. What is the magnitude of steady state error to a unit step input? Okay, there is this question. Then I have a unity feedback system with closed loop transfer function as this. Steady state error with respect to unit ramp input does. Okay. What does a ramp transform to at this stage? What does a ramp transform to? 1 over a square. Yeah, in fact, I could have technically written it initially itself. When you set Laplace transform, delta t transforms to 1. So far, we have used that. U of t transforms to 1 over s. We also used that. Helps you to know one more thing, that is ramp. Ramp is essentially t u of t. Transforms to 1 by s square. A linear function. If you draw it, it's going to look like this. This is non-zero for positive values of t, so this is a straight line. For negative values of t, it's not. It's it's multiplied with u, so this is 0. Okay, so you also know that. Okay, but notice there are two questions pertaining steady state error for a closed loop system. In 4 years, there are 2 years. There is a question on steady state error, and there is a question on steady state error. So what I'm going to do next is to explain you some basics of a feedback system, basics of a transfer function corresponding to a feedback system. You have to look at closed loop system, you have to look at a feedback system, unity feedback system, you have to look at a also look at a non-unity feedback system, and then what is steady state error. But most of the tools we need are already there. You don't need to know something new. That is a nice thing. Okay. So I'll explain transfer functions of feedback systems. I'll solve these two questions and then we'll stop. Okay. But notice there are more questions on Laplace transforms. Okay. So function is derivative of f, and Laplace transform of f is given. Okay. What would be the initial value of g of t? So you have to use this property. Derivative will be like, you use a couple of properties, but there are some issues with the, there are some issues with the answer key here. So I'm going to skip this. Then what is a bilinear transform? That is, can you go from yes to yes? It's technically a signals and systems question, but this was like a outlier. So I thought I would put it in controls discussion. Okay. Uh, Let me also, if you know how this transform is defined, this is fairly easy. Let me skip this one at least, or I can visit back, get back to that during signals and systems. This question, for a linear stable second order system, unit step response is such that peak time is twice the rise time, then the system is. This is hard, okay? That is this hard. It is involves recall, a lot of recall. I'm going to skip this, and then this question, a state-based model of the system is given this conditions for controllability and observability. This is kind of, at least considered to be out of syllabus right now. This is not basics of transfer function. Okay. So 2020, they just mentioned, they did not explicitly say transfer function. 2020, they said basics of control system. So they asked what is a controllable, what is observable, and all that. But right now, because they explicitly mentioned this is only transfer function, okay, let's say this is out of syllabus for 2025 syllabus, and if they don't change the syllabus, it's expected to be out of syllabus. So let's kind of not discuss this. It's fairly easy. Answer is fairly easy, but technically, let's say it's not in syllabus. So now let's solve these two questions: unity feedback system, non-unity feedback system. In fact, let's kind of arrange things. Yeah. We'll discuss those two questions and we'll wind up. And I'll discuss some minimal theory required to solve this. Okay. I'll try to make it as approachable as possible. Okay. We'll do one thing at a time. So, first is closed loop transfer function. So, initially, you have this system, right? We have an input that gets acted upon by a system with a transfer function h of s. You get the output, right? So, this is what we refer to as open loop. There is no loop A. You take this x of s, gets acted on or multiplied by h of s, you get y of s. Okay. So this is open loop. And in controls, conventionally we refer to the input and output by different names. Okay. So let me use that terminology. You have R of s giving C of s. Okay. You have the input R of s giving the output C of s. Okay. And I can benefit from some space, getting a little more space. So your RFS gets converted to C of S. You have your input, you have your output. Of course, here you have your input, here you have your output. Shortcut, okay, short form, output, input. I or B, what is I, what is B? It's just input, output, okay. Now, this typically gets acted upon by a transfer function again. So there is a G. Okay. The transfer function in controls typically is referred by symbol G. Might look like your C of S is a car. You multiply G, you get that, but no. You have to be careful. You also give a feedback here. That is, you see where the result is, you sense it. Okay, it's not a monologue. You talk to the students interactively, see where they are, and then accordingly modify things. Get feedback and also consider that in your action. You give a test, you sense, you analyze your result, and take appropriate action considering that analysis. Corrective action, right? If you don't analyze your test, give one test, revise, give another test, that's open loop. It's not effective. Give a mock test, analyze your results, see what is going wrong, try to improve those aspects, and act accordingly, right? Make your actions, feedback your past errors, right? That is a much better system, and that's what we are going to have. So you're going to feed it back. Okay. And for stability reasons, we are going to feedback, we are going to send in um, we are going to give a negative feedback. If there is an error, you want to decrease it. Okay, that's why you have this minus sign, sort of. You want to stabilize this feedback. So automatically I got a closed loop transfer function. Notice. So your C of S is no more R of G. Your task is to find what the C of S is. Okay. And at this stage, what is going on? You are going to, of course, add what is the output. You are taking the output, you are adding it. Okay. So you have to do some summation over here. So let's put this symbol over here. You are adding what is coming out here and what is going in over here. Okay. Again, I said I would benefit from some real estate. So I have a G. This is going there, and I am taking feedback. I'm taking the output and feeding it back to the input, negatively feeding it back to the input. Okay, let me mark a couple of points. What is the function signal that I get at the green dot here? Can you even say what is the function that is at the green dot? Imagine, you can quickly think of this as electrical circuit. Okay, what is the value at the green dot? What function is at the green point? RFS. Yeah, that is going in there, right? That is going in there. That is going into the summer. What function is there at the brown dot? Big surprises. That is just your output CFS. Okay. That function is also here. That function is also here. Anywhere over there, the value of that function, say equipotential wires or something like that, the value there is CFS. So what comes here, right? That happens to be the output. Of course, we are taking the output and somehow sensing it and considering that in your subsequent action, right? So we are feeding it back. Yeah, we are feeding back the output. So this is all CFS. I can write CFS over here. Can anyone say what is the value here? After the summer, this is going to add this and this with appropriate signs. Can you someone say what is at the yellow? R of S is coming. You are subtracting C of S. This happens to be R of S minus C of S. Okay. So at this stage, I'm going to go, I really need some space. So I'm going to go to the next page. But somewhere I also need to shift gears, okay? I'll quickly do that. This is negatively fed. And what is showing up here is R of S, the input, right? What shows up here is R of S minus C of S, right? Because what shows up here is C of S. What is here is C of S, right? And what shows up here is, so this goes through a transfer function of G. For simplicity's sake, I'm also going to drop that all of these are functions of S. I'm going to drop that, okay? So this is R minus C that is showing up here. What shows up here is take R minus C, transfer it by G. It has a gain of G. The output is input times this transfer function G. Input into output, right? For this local region. That's all I have done, right? So what shows up here is take R minus C, multiply that by a gain of G, or multiply that by the transfer function of that line, of that edge or subpart, whatever you want to call it. All this I'm doing to find one thing, that is, hey, for an open loop system, your H of S, the transfer function is Y of S by H of S. Your transfer function for open loop system, again, let me drop the yes and all that, okay, at this stage. H of S is Y by X. What you're trying to find is, hey, what is ratio of output to input here? You're trying to find that, okay? Notice we almost found it. Good news. The output essentially equals same as R minus C acting on G. I'm going to take, notice your output C of S. In fact, if I have to write it the way this is fed, just for clarity, your R minus G, sorry, R minus C acting on G happens to be your output. This happens to be your output. You can quickly find out what is C by R here. So you have RG minus CG equals C. Okay. Now this implies RG equals C into 1 plus G. So there you got it. Your C by R equals G by 1 plus G. I haven't done anything really, advanced, some simple algebra, right? The figure was also kind of easy to follow along. The transfer function, that is, if I have to represent this whole closed feedback thing into condense it into like one thing, what is the transfer function of that? G by 1 plus G. Okay. This is one important thing. So now, what is the point of this? Notice, if you know G, if you know R, you can find the output. That is, for a given input, you can find the output. R is, typically this is step, ramp, and all that. So given a transfer function, given what type of input you are dealing with, you can find the output, right? Typically, these are specified. Once you know output, of course, you can find the output transform of the output you have it. You can do inverse Laplace transform, perhaps by separation of parts, right? And then you can find the output as a function of time also. Okay. So, and let me also, give a name for this R minus C. R minus C is defined as, again, I don't want to complicate it because depending on whether there is unity, non-unity, and depending on the book that you're referring to, there can be some conventions, but let's call this as the error. Simply the error. Difference between input and output. Difference between the intended output and the deliberate input. Okay. Okay, so we have most of the things. I'm just only going to summarize what you have read so far. So notice your C is or G by 1 plus G. Okay. And then your R minus C, okay, equals R minus your error E happens to be R minus C, that happens to be R minus RG by 1 plus G. this equals or by 1 plus g. What this says is C of s can be found given R and G. What this says is error can be found given R and G. Two things of interest. Hey, what is the output for a given input? What is the error for a given input? Two things of interest, right? Or things on course or things are not going on course. Okay. Things, is the train going in the track or is it going out of track? Right? Is there a error? Right? And where is it going? Those two things we need to know. Those can be found given the system that you are dealing with and what kind of input that you are dealing with, correction that you are dealing with. Okay, this is all. In fact, this is what basics of transfer function for a control system is. Closed loop control system is closed loop transfer function. Okay, this goes by the name CLTF, closed loop transfer function. Okay, this goes by the name CLTF, closed loop transfer function. The G is open loop. G is that OLTF. This is closed loop transfer function, and then you have the error, you have the input output, the basic terminology. All of that I kind of explained it here. Now let's go back, solve one of these PVQs. Consider a unity feedback system, and by typically when they say feedback system, this is negative feedback system. You can take that for granted. Okay, we are not dealing with positive feedback systems. With closed loop transfer function, that is ratio of output by input is this. The steady state error with respect to unit ramp input is. This line says R of S is 1 over S squared. That is, your R of T happens to be T U of T. It's a straight line, a ramp. It looks like this. It looks like this. Okay. And that goes to 1 by S square. Okay. So your R of S, that line over there says you're dealing with R of S happens to be 1 by S square. Delta to 1, U to S, 1 over S, and then straight line to 1 over S square. So what they have given us directly, let me write that one also. This is closed loop transfer function. So what they are given is they are given C by R. Okay, that is G by 1 plus G, but they are given C by R. What you want is steady state error. Your error E of S, by definition, this is input minus output. What you intend minus what you get. By definition. Okay, what they want is E of infinity at steady state after a long time. There I gave you all the clues needed. So this happens to be R of S into 1 minus. Let's drop the yes. Okay, yes, it's kind of into 1 minus C by R. I just pulled out an R. because this term is given in the question. This term is given in the question. So you know the Laplace transform of a function. You want you want the function value at a specific, at a very convenient value, that specifically you want it at infinity. How do you find this? What is this e of t? How do you find that? What is e of infinity? That is a capital E, this is a small e. What is this difference? Of course, these two are transformed. This is in the time domain, that is in the Laplace S domain. You want e of infinity, okay? Small e of infinity. Final value theorem, okay? Great. So this happens to be, how do you get that? Of course, at this stage, FVT, right? This happens to be limit tending to 0, S times this thing. Let's also give some colors. Call this R. So there is an S from the final value theorem. Then R happens to be 1 by S square. And then you have 1 minus C, that is given to be S plus 90 by S square plus 10S minus 90. Sorry, plus 90. Hey, this is fairly easy to deal with. This is just S square plus 10S plus 90 minus S minus 90. You substitute S equals 0 and simplify this. In fact, later on, if you're slightly confused about the, anyways, I'm going to go to the next page. So yeah, this value happens to be 0.1. Okay. For everyone's clarity, let me do that. I have to go to the next page. E at infinity happens to be limit S tends to 0, S 1 by S square into S square plus 10S plus 90. Okay. S plus 90 minus S minus 90 by S square plus, hey, this actually S is tending to 0. So this is, it looks big, but most of it is 0, right? So, don't get disheartened by this. So this is square cancels. Okay. Fortunately, this 90 also cancel. That means, okay, this is limit. At this stage, you can see the answer. Okay. The SCS will also cancel. That SC also cancels. Okay. With the S tending to 0, what is left, all of that will cancel. This will cancel. This will cancel. This will cancel. Okay. All mostly 0. What is left is 10 by 90. Okay. There is a 1 here. Be careful. There is a 10 here and there is a 1 here. So what is left is in by 90, that happens to be 0.1. It's mostly zero, so you don't have to know. This is not something big. Okay, it's mostly zero, so it's fairly easy. So this answer is 0.1. All we did is, what is the definition of error? We use the final value theorem. Two things make out the answer. The transfer function is directly given here. How can they complicate it? Okay, they can give a g instead of c by r. If they want to slightly modify this, g of s can be given instead of, to modify this, a variation of this. Okay, question from the same concept. Typical variation. Typical variation. Give g of s. Give g of s. Give this function 1 by s plus 3, something like that. Give it instead of c by r as they gave it over. How do you deal in that case? Then what do you do? Then, in this case, c by r is just g by 1 plus g. And then you can just do what our problem that we did right now. That's a typical variation. This case, if this is given typical variation, if this is given, just your c by r is g by 1 plus g, and then proceed as above. Again, this is doable. It doesn't consume a time, which is why I'm discussing. And also, whatever theory needed for it is over there here. Okay. And yeah, there is some confusion on some terminology. Is this error? Is this actuating error? Right. For this discussion, to keep things simple, let's not consider that. For a non-unity feedback system, hey, you are feeding back -1. If it were not -1, if there is something on the way, what do you do? Says this, let's take the well-known thing. Again, I might have, it helps to get some real estate, okay? So let me give some space. This is the system that we saw. Let's recall we had an input here. We are taking the output here. There was a open loop transfer function. There was a gain here. And we fed back a -1. This is a summer, right? This X is a summer. To make it look better, we can put that -1 over here. This reverse path has a gain of -1. You can also, the same, this is what we saw earlier. For a non-unity feedback system, this is not in fact, again, it's convenient to put this as 1 and a negative over there, okay? And put the negative over there at the summation end. For a non-unity feedback system, this gain in this path, the gain is not 1, it's non-unity. It's some other function. Let's call it h. H, of course, is the function of s. All of these are functions of s. Okay, so this is a function of h. I'll give you 2 minutes. Can someone quickly find out what is what is a transfer function for this? What is c by r for this? Can you quickly find out? I'll give you about 2 minutes. Okay, so I already got an answer. Hopefully, it's not from recall. Okay, in the exam, preferably this is from recall. But right now, this is not from recall. Okay, in fact, this is an important relation. Let's give it some color. C by R for this case happens to be G by 1 plus GH. Can we quickly see that here? Sir, if in the exam I kind of forget this, can we quickly derive this? Yes. So you have C here. Okay. You have CH over here. You have R minus CH over here. You have R minus CH acting on G. That is happens to be your C. And you can quickly get C to the same side and find out what your C by R is. Right? Notice this implies C plus GHC. Okay, that is C into 1 plus GH. C into 1 plus GH equals RG. You can easily find what is C by R, that happens to G by 1 plus GH. So with this figure, you can easily write it down. In fact, to make it little more readable, this is R minus CH acted by G. And of course, that happens to be your C. Just solving that, you can get that relation. So which is what I mentioned, right? They need not give C by R directly. They can give you G of S instead. Hey, they made a small change here. This is a non-unity feedback system. So they gave both G and H. Okay. E. I'm not going to complicate things. There is a complication here. E is just R minus C. This is R into 1 minus C by R. Okay. What you want is steady state error for a unit step input. This is your R S is 1 by S, and the required answer is steady state error. You want E of infinity. Okay, notice, so your E of infinity, write down the theorem directly over there. E of infinity is limit s tending to 0, s E of s. Okay, that happens to be, so your E of infinity equals limit s tending to 0, s times r is 1 by s. Okay, this r is 1 by s times that thing. We know what is 1 minus g by g plus gh, right? So in fact, that's gh, say c by r. Okay. Again, this is s tending to 0. This is fairly easy to calculate. At this stage, let's remove this, these two cancels. Can you find a smaller line? Yeah, this cancels with this. So we have to find s tending to 0, this ratio. Okay, I'm going to do that in the next page. Technically, this is kind of exceeding my 1 hour, sorry, 1 page rough sheet suggestion, right? Don't spend more than 8 minutes in any one problem. But if you can recall that in a non-unity feedback system, transfer function is g by 1 plus closed loop transfer function is g by 1 plus gh, you can technically do this in 4 or 5 minutes. Okay. That too, it's s tending to 0. So it doesn't take a lot of time. You can technically do it. And yeah, although my rough work is exceeding 1 page, this is still doable. Okay. So I'm going to go to the next page. Let me get some details. G is 12 by s plus 2. H is 2 by s plus 3. Okay. Just give me 1 second. G is the, or H is this, that is 2 by s plus 3. And what I want is E infinity at this stage is 1 minus c by r equals 0. Okay, this is what I want. See, in the exam, this is what you're going to do. Okay. In fact, given this information, this also I can technically write it down here. You know G and H, right? E at infinity, and your R of s, of course, is 1 by s. Hey, some of this looks like delta. Okay, this is just this is limit s tending to 0, s into 1 by s into 1 minus 12 by s plus 2 by, okay, 1 plus 12 by s plus 2, okay, into 2 by s plus 3. And we cancel this yes with this yes. Okay. Can you substitute s tending to 0? Can we, I think this is easy to find, right? Can you find what this is? And so if I put that, notice this is 0, this is 0. It's all zeros, okay? There are no singularities, okay? I don't need any complicated. This is just, there isn't any singularities involved. This is fairly easy to calculate. This happens to be 1 minus 12 by 2 is 6 by 1 plus 12 by 2 again is 6, okay, into 2 by 3. Okay, and this happens to be, yeah, this is, some of this is fairly easy, right? This is, cancel this with a 2. So that is 1 minus 6 by 5. Okay, minus 1 by 5. That is minus 0.2. And what you want is the magnitude. So the answer is 0.2. Okay. Hey, this is fairly easy to do. This is, so, calculations exceed 1 page. What you're going to do in the examination is only this 1 page. Okay, extending to 0 of this is fairly easy. You have the G here, you have the H here. Okay, this is what you will do in the examination. You won't do this page, right? This is for my explanation. What you'll do in the examination is only this. That is still under 1 page. You can technically do that. Okay, so this happens to be minus 1 by 5. The magnitude of that is 0.2. And this 1 page is doable. And then we go to, there is somewhat of a problematic question. This is still what this appears to be initial value theorem, but this is somewhat problematic because some of the conditions required for the initial value theorem is not necessarily met here. The order of the numerator and the denominator, especially if you have a derivative here, you will have to multiply by s, right? Then this is second order in numerator, second order in denominator. Things get slightly complicated. You cannot use the initial value theorem, so you'll have to do that separation by parts and then integrate it. And then the question is whether when you do Laplace transform, is it going to be minus infinity or one of the terms will be clinging. You have to be careful. Okay, so I'm not going to discuss that. In fact, f of t transforms to f of s. Okay, g of t equals df by dt transforms to sf of s. Okay, and there is this minus f of 0, which is not given. But anyways, fine. This transforms to this. But notice this function sf of s into 1 plus s by square plus 12s plus 32. There is a power of S power, highest power of S is 2 in the numerator, highest power of S is 2 in the denominator. IVT may not apply. IVT doesn't apply. Okay. This is, in fact, let's write this as S square plus S. Okay. So for IVT and FVT, of S, order of N of S, order of numerator, okay, should be less than order of denominator, which is not the case. They are equal. Okay, this has to be strictly equal. This has to be strictly less than. There is no equal to here. So you cannot apply FAT. Or in this case, this is IVT doesn't apply. This is one of the required conditions. So what you have to do is you have to actually, split this into parts and, split it into parts and partial fractions and integrate. Okay. So what you're supposed to do is then take this um, partial fraction and first Laplace transform, like we did the differential equation question. Like we did here, you have to split it into parts and do that. The only thing is, when you do that, only problem in that case is when you do that, there will be a constant 1 because of S square, there will be a constant. When you take inverse Laplace transform of that, you will get a Dirac del of t. What is the value of del of t at t equals 0? Right? Only the integral is defined, del of t is not defined. So you run into trouble. Okay, there is a confusion between option D or, I think answer key is minus 17. So there is a confusion applying. Okay, but this is complicated. So at least the power of numerator should be less than the power of the denominator to apply the IVT FET. At least know that condition. Okay, this is one example where it doesn't apply. Know that much, and this is somewhat complicated. Even the answer key can be contested, I think. Okay, so with that, we are done with easy medium questions. Out of syllabus, we didn't do time response of second order systems. This is, you need to know a lot of recall. If your head is slightly spinning by now, control systems is no more, additional control systems is certainly not for you. But whatever we discussed here, those marks are certainly scoreable. Okay. And so I think most of the INEE students who are giving the exam will easily score that. Okay. At least they'll get 2 questions out of, say, on an average 3. So if you don't know, biomedical students, even some doctors, if you don't get those 2 questions in the examination, you're going to give an edge to IN students, right? Because they're fairly easy. It's cakewalk for them. Okay. So you don't want to give that edge, and hopefully with this video, whatever you learned in this one video will certainly help you to not miss that edge, to not give that unfair advantage. Okay. IN students, okay, even if this is not there, I learned something new. Okay, that is fairly, good. Would be happy to know that. But biomedical students, you need to know at least this much. At least that much that makes your head spin, at least for the first time. Okay. Second time, it kind of gets easier and easier. Right. Anyway, so this is recorded. You can watch it again and again. So don't miss that edge. We have certainly learned that much. And that was the objective. And this is a good place